All right, everyone. So nice to see some more faces in person. Got the usual two, Mr. Burrito Man over here. And we got a new person in here, so it's so cool. Anyways, so today we're going to go over quantum numbers. Has anyone started learning about quantum numbers?
Our mom's video is up.
That's great. So now you should know what we're talking about. Okay, well, if you don't know what we're talking about, then hopefully by the end of this session, you have an understanding of what we're talking about. So before we start, are there any questions? On Zoom, in person? No, yes, maybe, so I don't know.
No.
Okay, no questions. All right, so let's get straight to it. No sugar coating. It's gonna be a rough day with quantum numbers. No, I'm just kidding. It's not that bad. So the first quantum number we learn about is, it's not actually a number, it's a letter. It's the N quantum number. And this is actually what's referred to as the principal quantum number. And what this is actually associated with the energy level at which the electron is on. So when we're talking about quantum numbers, we're not talking about atoms as a whole, we're talking about specific electrons. So for example, let's just say we have our nucleus here and our first energy level, our second energy level, and our third energy level. So we know that the principal quantum number N is associated with the energy level. So if we're talking about an electron, let's use our electron in red. If we're talking about an electron on the second energy level, then the N value for that, the N quantum number for that electron is N equals 2. So for this electron, N would be equal to 2 because it's found on the second energy level. Let's say we had something that was on the third energy level. Well, that is N equals 3. So the principal quantum number is just associated with the energy level at which the electron is found on. So we know, and a rule for the N principal quantum number is that N can be any integer 1 to infinity. So I think in chemistry, and what we've seen in chemistry is N can only go up to like 7 so far, but theoretically N can go from 1 to infinity. So it can't be infinity, first of all, if that's what you're about to ask, but it can be any integer. What's up?
I was gonna ask like why we don't see like an N value of like 1.5 or something like that.
So because you remember when we talked about the Bohr's model of the atom, and they figured out that the atom or the electrons are quantized, meaning they can only be discrete energy levels. That means the electron can only occupy N values of 1, 2, and that means you won't find. Let's make this bigger again. If it can only occupy those whole integers because it's quantized, it means that you can't find an electron. You will never find an electron between these two between these two energy levels. It's either on 2 or on 3. You're never going to find it between the two or 3. So that's why you're never going to find an N value of 2.5 or something, because it's quantized. It can either be 2 or 3, or it can be 1 or 3. They just go by whole numbers, and that's what they discovered using some experiments back in the day. I'm not sure what they were.
So whenever they jump, it's like instant from like.
Yeah.
Okay.
It goes from 1 to 3 or 1 to 2, and there's no intermediates. It's never going to be 1.5 at any time. It's weird stuff. Once you get it down to that, yeah, it gets pretty weird.
Thank you.
Yeah. So that's the rule for our N quantum number. So N can be anything 1 to infinity, obviously not infinity though. So any questions about the first one before we go on to the next one? There's no questions. We'll be happy to go to the next one. So the next quantum number is L. So that's our cursive L. And what the L quantum number is, it's our angular momentum quantum number. And to be completely honest, you don't need to know what this means. This is something you would learn in a physics course later down the line. You don't need to know why it's called angular momentum quantum number, okay? That's something later. And that's the name of it. And there's also another name that you may see, azimuthal. So it may also be known as I don't even know how to pronounce the azimuthal quantum number. So you may see it as that. I've seen MCAT style questions where they use this in the name instead of L or angular momentum quantum number, just because it's a lot quicker to say this than it is to say this, right? So, you got someone with the camera, first time ever. Okay, great. So what L refers to is the type of orbital, and we have the types of orbitals range from s orbitals to p orbitals to d orbitals and f orbitals. So we'll learn this a little bit later, but s orbitals are spherical, so they go around the nucleus in a sphere. P orbitals, they're like dumbbell shapes, and d orbitals, this is where it starts getting really weird. I don't even want to draw it because I'm going to be honest, I didn't memorize them up to that far, because at this point they just start getting really ridiculously crazy.
The orbitals are like a flower, if you care. So there's like a circle in the middle, and then there's like 4 little.
Yeah, something like that, I'm sure.
That's definitely not that.
Okay. Anyways, we'll get into what these orbitals mean. So orbitals are just where electrons are found. Interesting. Yeah, okay. So we realize back in the day, they said that atoms look something like this, right? We have these orbits and they go in circles or whatever, but they're actually orbiting, but that turns out to not be true. Electrons don't occupy orbits. They're not in orbits around the nucleus. They're actually found in what we call an orbital, which an orbital is just a mathematical equation of the likelihood of finding an electron in a given area. So you don't need to really know that part. Just know like an orbital can, let's just say this room that we're in is the orbital, and you put an electron in here. At any point, it can be in any part of this room at any given second. It can be in that corner, next second it can be in that corner. That's basically what an orbital is. At any point, it can be in that one region of space, and they come in different shapes and sizes. Now, for the rules of the L quantum number, the angular momentum quantum number, so L can be any number from 0 to up to n-1. That means L cannot equal 1. So say we have an n value of 3. What are the possible L values for a quantum number of an electron? So it can be 0 to n-1. So 3 minus 2. So it can, yeah, exactly. So it can be 0, it can be, I'm gonna put or, it can be 0 or 1 or 2. You're never gonna see a combination. It's either gonna be 0, 1, or 2. And those are the possible L values, angular momentum quantum numbers for an electron in the third energy level. Again, so it can be 0, 1, or 2. It can't be a combination. You can't say n equals 3, L equals 0 and 1. It's either 0 or 1 or 2 for n equals 3.
It can't be -1 or -2.
That's m sub L, not L. L can only go from 0 to n-1. And when L is equal to 0, we're dealing with an s orbital. So let me make sure this is nice. So that's an s. So that's what the orbital we're dealing with when we're looking at L equals 0. If L is equal to 1, we're dealing with a p orbital. If L is equal to 2, we're dealing with a d orbital. And then L equals 3, we're dealing with an F orbital. So we'll get, it'll make more sense when we start actually talking about the like all 4 quantum numbers together. So at the end of this, we'll give you some examples. So this is where it starts getting a little confusing. Is there a way to memorize that? Memorize what, Derek? If you're trying to memorize this, put it into a flashcard and do it every day. Yeah, so if you're trying to remember what L equals 0 means and what L equals 1 means, like L equals 1 is P, L equals 2 is D, that's just gonna be straight up practice. Or just use some flashcards that you can find on Quizlet, I'm sure, or make your own. There's no really real way of going around that. Yeah, exactly, just study. Yeah.
Can't go over 3, right? Get 3 is the highest.
So if n equals 3, so if, let's say, if we're dealing with n equals 3, then L can only be 0 or 1 or 2. But if we're dealing with something like n equals 10, then L can be 0, 1 or 2 all the way to 9. Okay, so I don't want to go all the way, so 9. So in this case, L can be 3, but that's because n is 10 and L can only go from 0 to n minus 1. So the maximum, if n equals 10, if the principal quantum number is 10, then L can only go be a maximum of 9. Does that make sense? So L can be 3, but not in this scenario here, because n equals 3 and L can only go from 0 to what? N minus 1. If n, yeah, if n is 3, then L can only be 3 minus 1, which is up to 2. So that's the rule for, and like it says, L cannot equal n. So that's why in this case, it can't be 3, because if it's 3, if L is equal to 3 here, then that means L is equal to n, but that can't happen. If you're confused, ask questions, because it'll only get more confusing from here. So I want to make sure that there's no that you understand at least that.
So like if n was 12 and you go all the way up to 11.
Exactly. So the rule for n is that it can go from 0 to n minus 1, but it can never be n. So that's the way I think of it. So if n was 100, what are your possible values for L? 0 to 99, right? So it can be any of those. It's not going to be, it can't be a combination. It can only be one of those at any given time for a given electron. Yeah, what's up?
Will there ever be a way to determine what, or is it just gonna ask us like, which, like, say you're given like n equals 5 or whatever, and the question would be like, if n equals 5, what are the possible L values? Or would there be, are we gonna learn a way to like determine what L is?
Yeah, so when you learn about electron configuration, like the 1s2, 2s2, 2p6, you may be asked, let's see if we have a periodic table somewhere. I don't think, oh, here we go. Yeah, I don't know why there's an alligator in here. That was weird. Okay. So this is our P substuff. Is there something else on the screen?
I looked a little bit like the alligator.
Oh, I didn't get the alligator. I have to. Is it gone now?
No, there's a word to the left.
Sorry, I think this was from last semester and I was trying to, someone asked me about like the greater than and equal, like less than signs. So I was telling them how the alligator eats the bigger thing, so like. It's not funny, guys. Okay.
It's hilarious.
Let's get back on topic, guys. All right, so we'll eventually learn that this is our S. We call these our S group because it's all these electrons occupy S orbitals. And this is our P group. So it may say, if you're, let me think of a question that would require you to know quantum numbers. It may say if you add an electron to a phosphorus atom, what L value will the orbital be that the electron goes into? And because this is our P's, it's our P orbital, we know that the L value for that would be L equals 1, because that's a really badly worded question. I promise they're worded better than that. I just don't have one off the top of my head. But we have plenty of those questions on the review that we'll go over at that time.
I mean, you could have a little bit of both, like you said, Rami, like which of the following is like a possible N value or L value or something. You could have those types of questions. Or it could be like these, which of the following quantum numbers is like violated by some principle or something. Yeah, and then if you have like, say your N value is like 4, your L value is like 6, that would like violate all the principles. But as Dylan said, we have plenty of practice problems and we'll cross that bridge when we get to it.
You got it. All right, so are there any more questions for our principal quantum number or our angular momentum quantum number? And Susanna said, so N can never be negative. I didn't get to answer that earlier, but yeah, so N can only go from 1 to infinity. So it can be negative, because think about what N is telling us. It's telling us the energy level at which the electron resides on. So if it's a -1 energy level, that doesn't really make sense when you think of it from a physical standpoint, right? You can't have something occupying a negative energy level.
I think it goes 0 to infinity, right? 'Cause you
Yes,
said one-
no, so N can go from 0, or no, N can only be 1 to infinity, not 0 though, because the first energy level we see is N equals 1. It's the first energy level. There's no such thing, I guess, as N equals
0 must be like the negative.
Well, I don't think so, because it's applying to an energy level. So
Yeah, I mean, these are all in reference to energy levels, so there has to be like an energy level present in order for us to talk about it. So something like N equals 0, it might be like, I don't know, it might be possible that it is a nucleus, but we don't really care about that.
yeah, because quantum numbers are meant to describe electrons. If you're not talking about electrons in your energy levels, then N equals 0. I don't think that's a thing. Maybe it is.
Not ever heard.
Not that I'm aware of though. All right, so our next quantum number here is our M sub L quantum number, which is our magnetic quantum number. And this is basically talking about the orbitals and their orientation. So the easiest way to explain this one here is using our N equals 2. We know that when N equals 2, L can equal what values? L can either be 0 or 1. When L equals 1, let's just say that's what we're dealing with now. The values for M sub L go from -L to +L. So let me see if I can do that. Yes, so the rules for M sub L is equal to -L all the way to +L. So in this case, L is equal to 1. So the values for M sub L is -1 to 0 to +1. And each of these numbers is an orbital orientation. So when we talk about L is equal to 1, what orbital did we say we were dealing with? What type of subshell? Did someone say P? Yeah, I think I heard someone say P. So when we're talking about L is equal to 1, we're talking about our P subshell. So this is referring to our P subshell. So we know that our P subshell, later down the line, we'll learn about our electron configuration, like 1s2, 2s2, 2p6. This 2p6 indicates that the p orbital can hold 6 electrons. And if it can hold 6 electrons, we know that every single orbital can only hold a maximum of 2 electrons. Why is this being like this? This is being very glitchy. So every orbital can hold a maximum of 2 electrons. So if a subshell can hold 6 electrons, that means it has 3 orbitals, right? Because that would give you, if each of those lines represents an orbital, that would give you 6 electrons total. So this is our p subshell. And it's what we actually know now is that it's actually broken down into 3 separate orbitals, which have 3 different orientations. So we call this our px, py, and pz. That's a z. So each of these orbitals, m sub l is identifying each of these. So this one may be -1, this one may be 0, and this one may be +1. So again, we're getting, it's like as we go down the list of our quantum numbers, we're getting more and more specific. So we started off with n equals 2, which says our electron resides on the second energy level. And within the second energy level, we said L is equal to 1, which means in that second energy level, our electron occupies the p subshell, right? So that's even more specific. And we said, well, within that p subshell, we have 3 orbitals. Our electrons can either occupy px, py, and pz, and they're denoted by m sub l equals -1, 0, or 1. So you can kind of think of this as the state you live in. This is the city you live in. This is the neighborhood you live in. And then we're going to get to the last one, which is going to be the exact house you live in your neighborhood. So that's basically how quantum numbers are work. The further you go, you get more specific on where your electron is, because that's the whole idea of quantum number. It's like the address of an electron. So let's give another example over here. I know this is very confusing, so make sure you ask questions if you have any. L is equal to 4. Or n equals 4, L equals 3. Now let's say L equals 2. And m sub L can be what? What are the possible values for that? So -2, -1, 0, +1, +2. Exactly, because m sub L can go from -L to +L, so -2 to +2. So what this is basically saying, on the 4th energy level, in L equals 2 subshell, what is the subshell that corresponds to L equals 2? Say it with your chest. Yeah, Derek said D subshell. So 4th energy level, I'm going to abbreviate energy NRD. This is our D subshell. And m sub L can be either of these. So let's just say, because m sub L tells you the number of orbitals you have, the fact that we have 5 values for m sub L, that tells us we have 5 orbitals in the D subshell, which is true. Let's just say our electron, we can have these electrons here. And let's say we want to talk about this one right here. We're only concerned about this electron for whatever reason. M sub L would equal 0. Okay. So again, we went from, we said n equals 4. So we're dealing with an electron on the 4th energy level that's in the D subshell, denoted by L equals 2. And we only care about the m sub L equals 0 electron, which would be this one right here. So again, it's getting more specific as we go down, and then the next one will get even more specific. So are there any questions so far? I told y'all this is a very confusing topic, so make sure you ask questions if you have any. But let me show you the diagrams of what the P subshells look like. So what I mean by we have different orientations of the P subshells is that our P, we said we have PX, PY, and PZ. So our PX, we said that P orbitals look like they're dumbbell, like a dumbbell, right? So P orbital X is located along the X axis. P orbital Y is not here somehow. Looks like it got deleted or something. And that's unfortunate.
You deleted it a while.
What did you say?
Like you deleted it a while ago.
Yeah, I just don't know if it's gonna be there. Yeah, I'll
Who
be-
cares about the y-axis, right?
Yeah, for real. All right, and P orbital Z looks something like this. But whereas P orbital Y, it must have got deleted, looks something, it would be along this Y axis. So again, the M sub L is referring to the different orientations of which the orbital can take on. So it can be in plane of the X, Y, or Z for the P orbital. And the last one's the most simple quantum number of them. It's the M sub S, which stands for the electron spin. It can either be plus 1/2 or minus 1/2. And so we know that in, let's say our PX orbital, we can have 2 electrons, but one of them must be spin up, so plus 1/2, and the other must be spin down, so minus 1/2. You can never have, Pauli's exclusion principle says that no 2 electrons can occupy the same quantum number. So by M sub S existing in the way that it does, in the orbital either has M sub S equals plus 1/2 or minus 1/2. You can never have 2 spin ups because that would give you the same quantum number. Because if they're in the same orbital, that means N, L, and M sub L are the same thing. And if they have the same spin, that means M sub S is the same thing. So that would be invalid because we know no 2 electrons can have the same quantum number. So let's see if we can find any problems. I know I had a problem like this. Okay. Give me 1 second. All right, so let's go ahead and do I think this was the worksheet that we sent out last week. Number 6, so think about the rules that we just taught. And see if you can identify what may be wrong with these quantum numbers.
They have the same MS value.
Or that
They both have the same MS.
I was giving y'all a couple seconds. Can MS be negative? Yeah, so we said M sub S can either be plus 1/2 or minus 1/2.
No matter certain line.
One day you're gonna get 2.
Yeah.
That's cool. All right, so what do y'all think it is?
I don't think any.
You don't think anything? What are these quantum numbers? Yeah, we went over them last Friday, Derek. I don't know if you were there.
Yeah, no option C in particular.
Yeah, look at C. That's a very like irrelevant one that you can cross off if you saw that on the test, right?
That's not relevant.
The Telecala-Pauli effect. All right,
At least his last name made it.
so what do we know about these 2 quantum numbers? Are they same? Are they different? Are they the same? Are they the same? They're the same, right? And what did we say earlier, that no two electrons can have the same quantum quantum number, right? Because if they do, that violates a certain principle that is called, I think you almost have it, a B, or not a B, but it rhymes with a B, sounds like P. That only gives you one other option.
Rhymes with Polly.
Yeah, option D.
Prestige.
And please, we're having a session.
I'm just telling you the prestigiousness in this room.
I feel it. All right, so what is Pauli's exclusion principle, Rich?
Paul's exclusion principle basically states that no two electrons can have the same set of quantum numbers. And since these are, well, the exact same as we've specified, then that means that this particular set of quantum numbers violates Pauli's exclusion principle, which corresponds to option B.
So this is one way you'll see the question asked. And the next way, if there's no questions, and if there are, just I'll go back up in a second. Yeah, basically like this. The next way. It's crazy. Let's see, number 8. Which of the following sets of quantum numbers is invalid? This is another way you would see it on the exam. So this would require you to recall all of your skills that you just learned about the rules of quantum numbers and how they are applied to electrons in atoms. Okay, we got one person with an answer. Give everyone else a little bit more time to see if they got something. Take your time, guys. Look at each one, identify the rules for each quantum number, and identify which one is invalid.
Be intentional. Take what's on it.
I haven't checked.
The column doesn't even exist.
That's weird. That sounds like not my problem.
No, I'm just looking at them to see, like, I usually just look at it, see what I have to do later. Yeah. I finished the outscoring stuff. I just did that.
Not more expensive to get rid of an iPhone.
Yeah, it is.
What is your birthday?
All right, Katrina got an answer.
All right,
So-
there is an answer of E has an elephant.
What did y'all say in chat? And don't be a follower. What did y'all actually think?
Am I allowed to speak?
Was I talking to you? Yeah, go ahead. What did you think, Rob?
I thought it was E because the ML value.
That is an interesting answer.
Astute observation, as Miss Bristol would say. Oh, no.
So let's see. Go ahead, Rich. Go through, go validate each one or invalidate. them.
All right, which of the following sets of quantum numbers is invalid? So gotta look here, option A, n equals 2 seems valid enough, right? Like, it's from 1 to infinity, 2 is between 1 and infinity, so we're good. L is from anywhere from 0 to n minus 1. So L can only be what, 2 values in this case? 0 or 1, shout out binary code, so it can either be 0 or 1. So L is 0, that's fine to me. M sub L, what's the only value M sub L can be? It's 0. If L is 0, M sub L is only 0. M sub S is -1/2, and that's what it is, like, yeah, so that A is valid. Now B, same deal, 4 to infinity, 1 to infinity, 4 is a number in between there, so we're good. And then L is 2, so what values does L range from for D? So it's actually 0 to 3. Remember, it goes 0 and then to 3, so like n minus 1. So 0 to 3, L is 2, that's between 0 and 3, so that looks good to me. Then M sub L is from what, -2 to +2. And 1 is in between those numbers, so that's good. And M sub S, +1/2, sure, cross that off. Then same deal here, n equals 5, sounds good. L, let's see, well, it's from 0 to 4, 1's in between that, so we're good there. M sub L, it's from -1, 0, or 1, it's good there. M sub L +1/2, cool. N equals 1, that's what the bare minimum it can be. L is 0, it's also pretty good to me. M sub L, the only other value can be is 0, and M sub S is +1/2, sounds good to me. So now by process of elimination, with option E, let's check it. N equals 5. 5 is a number from 1 through infinity, so that sounds good. L is 3, does that make sense? Why?
Because it can be 0.
0 through 4, exactly. Wait a minute. M sub L value. Looking kind of funky. Can anybody tell me why?
Go from -3 to +3.
Yeah, supposed to be from -3 to +3. In this case, it's only from, M sub L is -4, which doesn't fall within that range. And M sub S, we don't care, still +1/2. So that corresponds to option E. All right, let's think of another problem. I'm gonna give you all a bit of a toughie. If I do say so myself. So. Right. Okay, right, which orbital this electron belongs in? Your N is gonna be 5. Your L is gonna be 3. Your M sub L is gonna be -2. Your M sub S, let's make it +1/2. Yeah. Let's give you all 2 minutes, and if you're done with that problem, figure out what's wrong with this quantum number. N equals 2, L equals 1, M sub L equals 0, and M sub S equals -6.
It's fine.
All right, if we're done with that one, we'll work on that. And if you're done with that one, tell me what's wrong. Tell me what's wrong with this.
We're trying to work on the other one still. That looks fine.
Yeah.
Okay.
Tell me what's wrong with that. So 3 problems. 1, 2, 3.
Right, it's gonna shoot. I can write it.
I don't have to write it down. I'll let y'all work for a little bit.
You're trying to share your problem.
Wait, you don't even need.
Yeah, but it just takes. All right, everyone have an answer?
Are all three of these questions?
Does the MS really matter much? Cause you kind of just went through it and be like, oh,
No, it really doesn't. Remember, it can be either up or down. You know.
Try to find out. The question for one is, what's it called? The question for one, what was the question for, oh yeah, determine what orbital the electron belongs to, given the quantum numbers.
And Susanna, the significance of M sub S is that it can literally only be plus 1/2 or minus 1/2.
does that like represent?
It's representing the fact that no two electrons can have the same quantum number, because if you are in the same orbital on the same energy level in the same subshell, you can't both be spin up. You can either be one spin up or spin down, because if they're both spin up, then you have two electrons that occupy the same quantum number. So that's like the significance of M sub S. That's the whole idea behind M sub S is, oh, it doesn't work if they're both plus 1/2, so make one of them negative 1/2 and call it a day. Pretty much. All right, Rich, should be good.
Okay, all right.
No, Susanna, you don't have to determine M sub S based on the other quantum numbers. It can either be. So let's just looking at question or answer choice A on the left side of the screen. It could have said plus 1/2 or minus 1/2. Each of them would be valid. It doesn't matter. As long as it doesn't say plus 10 and minus 10, it's always either 1/2 positive or negative. So it's never going to be another number besides 1/2. So that's I guess the only rule. It can't be plus or minus 1. It has to be plus or minus 1/2. All right.
All right, okay. Somebody besides Rami, tell me what you got for the first problem.
What's wrong with this one here?
Or it's nothing wrong with it, just state the orbital in which it belongs. The what F, multiple Fs.
There's a lot of F orbitals or subshells. What energy level is it on? Which quantum number is the energy level quantum number?
Awesome.
So remember, there's one quantum number, and it might have been the first one we went over, that is the principal quantum number. That is, you remember these notes up here? That's not on this slide.
Would be 1 to infinity, but not infinity.
Now, you remember this? And principal quantum number is associated with the energy level. So if it's, go back to that other one. Exam 3, where was it? So if we're dealing with a subshell, an F subshell, and we're asking what energy level is it on, you should go look at what number to figure that out, what quantum number to figure that out. So the L equals 3 is, that's telling you that it's an F subshell.
What does that? Little wording threw me off.
So this is the F, and then what F orbital specifically?
I don't get what you're asking. What-
So, yeah, which,
1, 2, 3?
all right, so I guess what I'm looking for when I ask this is energy level plus like block. So like the block is either like S, P, D, or F. And then this is your
Oh, wait, this guy was just another shirt.
S, P, D, or F. And then this one is like 1 through infinity or N. So it's N plus L. That's what I call it. So it's the 5, what?
F.
Yeah, 5F.
There's it, right?
Yeah, so these quantum numbers belong to an electron in the 5F orbital. Later, you're gonna be asked,
This guy rich.
later, you're gonna be asked, what's it called? You're gonna be asked to identify an element based on what quantum numbers they are. Or you'll be given a quantum number and be asked to identify the element it comes from. So yeah, that's how you'd answer one of these questions.
In those cases, are we just to assume that the quantum number they give us is like, I guess the outermost electron, if that makes sense?
Yeah,
Yeah,
most likely. That's kind of the only way I see to do it.
Okay.
so in this case, if you were asked to identify the element, so we've already established that it's on the 5F or a subshell. And then you look at your M sub L right here, and notice that it can range from negative L to positive L. So if we look at our periodic table, the 5F orbital will be down here where your actinide series is, your AC right here. And this goes from what, negative L?
Don't worry about the emotions. This guy rich just exposing me, bro.
Yeah, so it goes from negative L to positive L. So likewise, you can go -3, -2, -1, 0, 1, 2, 3, and then repeat that again, -3, -2,
They
-1.
can't see, they can't see where you're pointing, Rich. So if you're gonna do it, you gotta turn around and point at the screen.
All right,
What about Zoom?
About.
right, let's-
No.
you got this stuff figured out. Okay, so 5F, so let's say this -3, -2, -1, 0, 1, 2, and 3. But then we gotta repeat it again. So -3, -2, -1, 0, 1, 2, 3, and let's put that as -3 for fun.
So it's just those bottom two rows?
Those are the F subshells, yeah.
Yeah, it's just these bottom rows, yeah.
That's the most sus pointer I've ever used.
In this case, it's, the M sub L is like -2, so we can say that this element is thorium right here, TH. So it's -3, and then this M sub L will be -2, because the way the electrons move, it has a proton, and then what's it called, the electrons, they move over to a different orientation. So like, I'm not too specific on the F orbital axes, but like, let's assume the first one was X and then the second one was Y. So it like rotates onto the Y axis.
Yeah, so. Let's see if these questions are. If you can get these, what is the maximum number of orbitals?
For the other question, do we just look at the N to get the, like, which orbital it's on, and then the L for the S?
Yeah, the N for like which like period it's on, and then L for like SPD or F.
So I want the number of orbitals associated with these quantum numbers. And you just have to. And we know that the number of orbitals are derived from which quantum number? M sub. You got two options, and one of them is definitely not the M sub L, right? Because like we said with the p orbital, or the p subshell, L equals 1, and for the p subshell, M sub L can equal -1, 0, or +1. And we know that the p subshell has 3 separate orbitals, and these 3 numbers denote the 3 separate orbitals. So there's 3 orbitals associated with L equals 1. So I want you to do that for each of these. Um, Yeah,
N and L can't equal each other, right?
yes, that's the point, man.
I thought you were just asking us to figure out how many electrons there were.
I said,
Ruined it.
what is the
whole
maximum number of
thing.
orbitals associated with these? And this guy wrong. Can't keep a joke to himself.
I'm sorry,
I've never invited you to a party, man.
I'll hinder my academic improvement for you.
You're the type of guy to spoil a surprise party, bro. Like, by the way, everyone's at your house waiting for you. Anyways, so these are 4 separate time, you know, I had a feeling you were gonna say that as soon as you said, hey, Dylan. All right, so these are 4 separate things. I want to know what the orbit, how many orbitals are associated with each one. So let's go with the first one. N equals 4, L equals 1. How many orbitals are associated with that quantum number? We just went over that the orbitals, the number of orbitals is determined by how many blank values there are. What was that blank that I just said right before? M sub L. So how many M sub L values there are determines how many orbitals there are. So M sub L for this one can be -1, 0, or +1. That means that there's 3 orbitals associated with these 2 quantum numbers. So the answer should have been 3 orbitals. And this one's a trick question. I wonder who got this one. I wonder if this one tricked anyone. What's wrong with number 2? Anyone? If there is anything wrong with it.
Well, everyone heard it.
Yeah, I know. I'm just hoping someone was not paying attention. Sorry. It's fine, Robbie, it's fine. You always gotta make your presence known. I'm just kidding. N and L cannot equal. So like Susanna said, L cannot equal N, and in this case, N equals 2, the valid L values for when N equals 2 would be L equals 0 or 1. However, L cannot equal 2, but in this case, L equals 2. So that's an invalid quantum number. Therefore, the amount of orbitals that are associated with this invalid quantum number is what? If this thing does not exist, how many orbitals can be? None, right? So 0. 0 orbitals. Because this thing doesn't exist. What about when N equals 3, L is equal to 2? 5 possible orbitals, because we go from M sub L is from -2 to +2. And because you have 5 separate numbers, that 5 separate values, possible values for M sub L, that means you have 5 orbitals in the L equals 2 subshell. What subshell does this correspond to? D subshell, yeah. Good job, Derek. Looks like you're already memorizing. So 5 orbitals. And what about this last one? How many orbitals are associated with that? Those quantum numbers. U in the front.
Did you not hear me? I said it twice.
I did not hear you.
I said 3.
Why 3?
Because L equals 1, so isn't it -1, 0?
L does equal 1, but it also says M sub L is equal to -1, which is specifically talking about a single orbital. Because remember when the possible L values are -1, 0, and 1. Each of these is an orbital. So you have 3 possible orbitals. But because we're talking about only one orbital is associated with that quantum number. So this last one would these 3 quantum numbers in total, they essentially define a unique orbital. It's talking about one orbital specifically. The only I guess the next thing up would be to assign its m sub s number, which is just either up or down, right? So this has already gotten you down to the orbital at which the electron resides in. Remember, this is like our state, this is like our city, this is our neighborhood, and the next one, m sub s, would tell you where your exact house is in that neighborhood. Let's see if there's no questions, I want to go to the next question. So write a set of quantum numbers. This will be the last one we do today. For F orbital. Rami, thoughts to yourself. I'm just kidding. You know what? I'll let you answer this. Okay. Let's get Rami. Let's get Rami.
He's the one that's stopping me.
Well, because I want other people to answer, because we get it. You
10 seconds of silence.
How about 10 minutes? I'm just kidding. Okay. So we're just sharing answers now, huh, Derek?
Oh, but when I do it.
Hey, but Derek actually is trying, man. He's a good student.
I just tried a little harder, which is why I got it first. Oh.
Yeah, Rainy. Dang. How do you spell your name?
Oh.
All right, so if you were able to get the first one is very easy. The first quantum number is very easy. If we're talking about the 4f orbital or subshell, we're talking about what energy level? 4f orbitals / subshell. We're talking about what energy level? What? Energy level 4, which means n equals 4. If we're talking about our F subshell, what L value are we referring to? 3. So if you don't remember these, you can always, it goes in order of S, P, D, F, and it starts at 0. So 0, 1, 2, 3. So that's how you could remember your L values if you don't want to do all the great memorization. And if we're talking about orbitals, we're talking about the m sub L, right? So what are possible values for m sub L? So you said -3 to, yeah, so -3 all the way to +3. So I'll just write them out. -1, 0, +1, +2, and +3. How many orbitals are possible for that? 7 orbitals, right? So you can have at least 7 different quantum numbers associated with that.
For the M sub L, you don't have to write down all of them, just pick one.
Yeah. So you could have done either of those, as long as it's a valid M sub L. So if you are still unsure about this, hopefully when you go to class and learn about this, it'll make more sense. And we'll continue to do problems with quantum numbers This is probably one of the most difficult topics to conceptually understand, and if you can, get it into your brain now, you'll be doing yourself a huge favor when you're studying for your MCAT or whatever. I don't even know, maybe this is on the DAT, I don't know. But no. But I've done some problems for the MCAT and no, I plan to. But yeah, so are there any questions before y'all? Before we go? If there's any questions about any of the topics, please feel free to ask. We'll be here for a little bit. And feel free to ask any questions. Is the worksheet pinned? No, but it was sent out last time.
Are you able to find the MFS,
What?
the MS thing?
You just pick one. You just either put -1/2 or +1/2. It does not matter. As long as you don't make it like 200 or something, you're good.
Read the textbook. I know, how many of y'all have actually read the textbook this semester? Probably none of it.
We have Alex.
Alex
Did
has
you
the
know
textbook.
that you have a textbook on Alex?
That is good, so
Yeah, time to read that with Alex.
So I quickly glance over.
yeah, just go to the topic you're struggling with.
Yeah, until it's
Hey,
due.
this is probably the only chemistry class that you're not gonna have to read the textbook for. So don't, I'm telling y'all, when you go to other chemistry classes, please don't do what you did this semester and not read the textbook, because the textbook is gonna be your way to learn in those classes. We're not even lying. We thought, oh, Gen Chem 2, we didn't read the textbook in Gen Chem 1, so we don't need to in Gen Chem 2. No, you got to.
Is that just because you didn't have Ramon?
No, I think even if I had Armand, I would still have to read the textbook.
Well, we're about to find out, because he's teaching the Gen Chem 2 class now.
Who is?
Not next fall.
It's like he took over for some reason.
Still hold up.
Yeah, is Jonathan? Is Jonathan here? No, Jonathan's not here. Hey Taylor, how's it going?
This guy Jonathan really said he'd pull up, but he's late. He said, I'm gonna be late. Proceeds to be late for 2 hours. This guy,
So wait, you said Thompson?
Thomas,
Thomas.
Susan Thomas.
Yeah,
She's the best for Gen Chem 2.